A transformer is an electrical device that transfers electrical energy between two or more circuits through electromagnetic induction. Electromagnetic induction produces an electromotive force across a conductor which is exposed to time-varying magnetic fields. Commonly, transformers are used to increase or decrease the voltages of alternating current in electric power applications. A varying current in the transformer's primary winding creates a varying magnetic flux in the transformer core and a varying magnetic field impinging on the transformer's secondary winding. This varying magnetic field at the secondary winding induces a varying electromotive force or voltage in the secondary winding due to electromagnetic induction. Making use of Faraday's law in conjunction with high magnetic permeability core properties, transformers can thus be designed to efficiently change AC voltages from one voltage level to another within power networks. Since the invention of the first constant potential transformer in 1885, transformers have become essential for the transmission, distribution, and utilization of alternating current electrical energy. A wide range of transformer designs are encountered in electronic and electric power applications. Transformers range in size from RF transformers less than a cubic centimeter in volume to units interconnecting the power grid weighing hundreds of tons. Basic principles. Ideal transformer equations by Faraday's law of induction. Combining ratio of and turns ratio, where for step-down transformers are greater than 1 for step-up transformers are less than 1 by law of conservation of energy. Apparent, real and reactive power are each conserved in the input and output. Combining and with this endnote yields the ideal transformer identity. By Ohm's law, an ideal transformer identity. Apparent load impedance ZL. For simplification or approximation purposes, it is very common to analyze the transformer as an ideal transformer model as presented in the two images. An ideal transformer is a theoretical, linear transformer that is lossless and perfectly coupled, that is, there are no energy losses and flux is completely confined within the magnetic core. Perfect coupling implies infinitely high core magnetic permeability and winding inductances and zero net magnetomotive force. A varying current in the transformer's primary winding creates a varying magnetic flux in the core and a varying magnetic field impinging on the secondary winding. This varying magnetic field at the secondary induces a varying electromotive force or voltage in the secondary winding. The primary and secondary windings are wrapped around a core of infinitely high magnetic permeability so that all of the magnetic flux passes through both the primary and secondary windings, with a voltage source connected to the primary winding and load impedance connected to the secondary winding. The transformer currents flow in the indicated directions. According to Faraday's law of induction, since the same magnetic flux passes through both the primary and secondary windings in an ideal transformer, a voltage is induced in each winding, according to IQ. In the secondary winding case, according to IQ. In the primary winding case, the primary EMF is sometimes termed counter-EMF. This is in accordance with Lenz's law, which states that induction of EMF always opposes development of any such change in magnetic field. The transformer winding voltage ratio is thus shown to be directly proportional to the winding turns ratio according to IQ. According to the law of conservation of energy, any load impedance connected to the ideal transformer's secondary winding results in conservation of apparent, real and reactive power consistent with EQ. The ideal transformer identity shown in EQ is a reasonable approximation for the typical commercial transformer, with voltage ratio and winding turns ratio both being inversely proportional to the corresponding current ratio. By Ohm's law and the ideal transformer identity, the secondary circuit load impedance can be expressed as EQ. The apparent load impedance referred to the primary circuit is derived in EQ. to be equal to the turns ratio squared times the secondary circuit load impedance. Polarity A. Convention is often used in transformer circuit diagrams, nameplates or terminal markings to define the relative polarity of transformer windings, positively increasing instantaneous current entering the primary windings. End induces positive polarity voltage at the secondary windings. End. Real transformer deviations from ideal. The ideal transformer model neglects the following basic linear aspects in real transformers. Core losses, collectively called magnetizing current losses, consist of hysteresis losses due to nonlinear application of the voltage applied in the transformer core, and eddy current losses due to Joule heating in the core that are proportional to the square of the transformer's applied voltage. Whereas windings in the ideal model have no resistances and infinite inductances, the windings in a real transformer have finite non-zero resistances and inductances associated with Joule losses due to resistance in the primary and secondary windings. Leakage flux that escapes from the core and passes through one winding only, resulting in primary and secondary reactive impedance. Leakage flux. The ideal transformer model assumes that all flux generated by the primary winding links all the turns of every winding, including itself. In practice, some flux traverses paths that take it outside the windings. Such flux is termed leakage flux, and results in leakage inductance in series with the mutually coupled transformer windings. Leakage flux results in energy being alternately stored in and discharged from the magnetic fields with each cycle of the power supply. It is not directly a power loss but results in inferior voltage regulation, causing the secondary voltage not to be directly proportional to the primary voltage, particularly under heavy load. Transformers are therefore normally designed to have very low leakage inductance. In some applications increased leakage is desired, and long magnetic paths, air gaps, or magnetic bypass shunts may deliberately be introduced in a transformer designed to limit the short-circuit current it will supply. Leaky transformers may be used to supply loads that exhibit negative resistance, such as electric arcs, mercury vapor lamps, and neon signs, or for safely handling loads that become periodically short-circuited, such as electric arc welders. Air gaps are also used to keep a transformer from saturating, especially audio frequency transformers in circuits that have a DC component flowing in the windings. Knowledge of leakage inductance is also useful when transformers are operated in parallel. It can be shown that if the percent impedance and associated winding leakage reactance to resistance ratio of two transformers were hypothetically exactly the same, the transformers would share power in proportion to their respective volt-ampere ratings. However, the impedance tolerances of commercial transformers are significant. Also, the Z impedance and X/R ratio of different capacity transformers tends to vary, corresponding 1000 kVA and 500 kVA units values being, to illustrate, respectively, Z 5.75%, X, R 3.75 and Z 5%, X, R 4.75. Equivalent circuit. Referring to the diagram, a practical transformer's physical behavior may be represented by an equivalent circuit model, which can incorporate an ideal transformer. Winding Joule losses and leakage reactances are represented by the following series loop impedances of the model. Primary winding, RP, XP. Secondary winding, RS, XS. In normal course of circuit equivalence transformation, RS and XS are in practice usually referred to the primary side by multiplying these impedances by the turns ratio squared, 2 equals A2. Core loss and reactance is represented by the following shunt leg impedances of the model. Core or iron losses, RC. Magnetizing reactance, XM, RC and XM are collectively termed the magnetizing branch of the model. Core losses are caused mostly by hysteresis and eddy current effects in the core and are proportional to the square of the core flux for operation at a given frequency. The finite permeability core requires a magnetizing current Im to maintain mutual flux in the core. Magnetizing current is in phase with the flux, the relationship between the two being nonlinear due to saturation effects. However, all impedances of the equivalent circuit shown are by definition linear, and such nonlinearity effects are not typically reflected in transformer equivalent circuits. With sinusoidal supply, core flux lags the induced EMF by 90 degrees. With open-circuited secondary winding, magnetizing branch current I0 equals transformer no-load current. The resulting model, though sometimes termed exact equivalent circuit based on linearity assumptions, retains a number of approximations. Analysis may be simplified by assuming that magnetizing branch impedance is relatively high and relocating the branch to the left of the primary impedances. This introduces error but allows combination of primary and referred secondary resistances and reactances by simple summation as two series impedances. Transformer equivalent circuit impedance and transformer ratio parameters can be derived from the following tests: open circuit test, short circuit test, winding resistance test, and transformer ratio test. Basic transformer parameters and construction. Effective frequency transformer universal EMF equation. If the flux in the core is purely sinusoidal, the relationship for either winding between its RMS voltage ohms of the winding and the supply frequency F, number of turns N, core cross-sectional area are in M2, and peak magnetic flux density B peak in Weber per square meter, or T, is given by the universal EMF equation. If the flux does not contain even harmonics, the following equation can be used for half-cycle average voltage EAVG of any wave shape, by Faraday's law of induction shown in EQ. And transformer EMFs vary according to the derivative of flux with respect to time. The ideal transformer's core behaves linearly with time for any non-zero frequency. Flux in a real transformer's core behaves non-linearly in relation to magnetization current as the instantaneous flux increases beyond a finite linear range, resulting in magnetic saturation associated with increasingly large magnetizing current, which eventually leads to transformer overheating. The EMF of a transformer at a given flux density increases with frequency. By operating at higher frequencies, transformers can be physically more compact because a given core is able to transfer more power without reaching saturation, and fewer turns are needed to achieve the same impedance. However, properties such as core loss and conductor skin effect also increase with frequency. Aircraft and military equipment employ 400 Hz power supplies which reduce core and winding weight. Conversely, frequencies used for some railway electrification systems were much lower than normal utility frequencies for historical reasons concerned mainly with the limitations of early electric traction motors. As such, the transformers used to step down the high overhead line voltages were much heavier for the same power rating than those designed only for the higher frequencies. Operation of a transformer at its designed voltage but at a higher frequency than intended will lead to reduced magnetizing current. At a lower frequency, the magnetizing current will increase. Operation of a transformer at other than its design frequency may require assessment of voltages, losses, and cooling to establish if safe operation is practical. For example, transformers may need to be equipped with volts per hertz over-excitation relays to protect the transformer from overvoltage at higher than rated frequency. One example is in traction transformers used for electric multiple unit and high-speed train service operating across regions with different electrical standards. The converter equipment and traction transformers have to accommodate different input frequencies and voltage while being suitable for multiple AC, asynchronous motor and DC converters and motors with varying harmonics, mitigation, filtering requirements. Large power transformers are vulnerable to insulation failure due to transient voltages with high-frequency components, such as caused in switching or by lightning. Energy losses. Real transformer energy losses are dominated by winding resistance, dual and core losses. Transformers' efficiency tends to improve with increasing transformer capacity. The efficiency of typical distribution transformers is between about 98 and 99%. Hysteresis and eddy current losses are constant at all load levels and dominate overwhelmingly without load, while variable winding dual loss is dominating increasingly as load increases. The no-load loss can be significant, so that even an idle transformer constitutes a drain on the electrical supply. Designing energy-efficient transformers for lower loss requires a larger core, good quality silicon steel, or even amorphous steel for the core and thicker wire, increasing initial cost. The choice of construction represents a trade-off between initial cost and operating cost. Transformer losses arise from winding dual losses. Current flowing through a winding's conductor causes dual heating. As frequency increases, skin effect and proximity effect causes the winding's resistance and, hence, losses to increase. Core losses. Hysteresis losses. Each time the magnetic field is reversed, a small amount of energy is lost due to hysteresis within the core. According to Steinmetz's formula, the heat energy due to hysteresis is given by, and hysteresis loss is thus given by, where F is the frequency, eta is the hysteresis coefficient, and beta max is the maximum flux density, the empirical exponent of which varies from about 1.4 to 1.8 but is often given as 1.6 for iron. Eddy current losses. Ferromagnetic materials are also good conductors, and a core made from such a material also constitutes a single short-circuited turn throughout its entire length. Eddy currents therefore circulate within the core in a plane normal to the flux, and are responsible for resistive heating of the core material. The eddy current loss is a complex function of the square of supply frequency and inverse square of the material thickness. Eddy current losses can be reduced by making the core of a stack of plates electrically insulated from each other, rather than a solid block. All transformers operating at low frequencies use laminated or similar cores. Magnetostriction-related transformer. Magnetic flux in a ferromagnetic material, such as the core, causes it to physically expand and contract slightly with each cycle of the magnetic field, an effect known as magnetostriction, the frictional energy of which produces an audible noise known as mains hum or transformer hum. This transformer hum is especially objectionable in transformers supplied at power frequencies and in high-frequency flyback transformers associated with PAL system CRTs. Stray losses. Leakage inductance is by itself largely lossless, since energy supplied to its magnetic fields is returned to the supply with the next half-cycle. However, any leakage flux that intercepts nearby conductive materials such as the transformer's support structure will give rise to eddy currents and be converted to heat. There are also radiative losses due to the oscillating magnetic field, but these are usually small. Mechanical vibration and audible noise transmission. In addition to magnetostriction, the alternating magnetic field causes fluctuating forces between the primary and secondary windings. This energy incites vibration transmission in interconnected metalwork, thus amplifying audible transformer hum. Core form and shell form transformers. Closed-core transformers are constructed in core form or shell form. When windings surround the core, the transformer is core form. When windings are surrounded by the core, the transformer is shell form. Shell form design may be more prevalent than core form design for distribution transformer applications due to the relative ease in stacking the core around winding coils. Core form design tends to, as a general rule, be more economical, and therefore more prevalent, than shell form design for high-voltage power transformer applications at the lower end of their voltage and power rating ranges. At higher voltage and power ratings, shell form transformers tend to be more prevalent. Shell form design tends to be preferred for extra high voltage and higher MVA applications because, though more labor-intensive to manufacture, shell form transformers are characterized as having inherently better kVA to weight ratio, better short-circuit strength characteristics and higher immunity to transit damage.